So we covered the negative binomial. We discussed these model evaluation tools. So I think the only thing I want to add for today is to reflect a little bit on the implementation of a zero inflated model or a zero truncated model, and to give you an idea on how to do that, right? So we know from the course material that one of the things why we sometimes want to adjust basic count distributions is because they're not so capable of dealing with the large number of zeros typically encountered in claim frequency data. And we discussed the idea of zero modification and zero truncation. So in the literature, we often call zero modification, we refer to that as a zero inflated distribution. So that means that you build a mixture of a regular count distribution and then a degenerate distribution with all its probability mass at zero. And you give a weight, here denoted with P, to this degenerate distribution at zero, and you give the weight 1 minus P to the regular count distribution. And that basically means that you change your probability function in the following way, right? So that's a zero inflated count model. It's a two-component mixture model. It combines a point mass at zero with a proper count distribution. If you look at a zero truncated distribution, what I call a zero truncated distribution here, it's what I'm gonna do is, but I just wanna make sure, so what I refer here to zero inflated, it's a mixture of a degenerate distribution at zero and a regular count distribution. And what I'm gonna do here is I'm gonna create a mixture of a degenerate distribution with all its probability mass at zero. And then I'm gonna mix that with a count distribution, but a count distribution that is conditional on n being strictly larger than zero, right? So here I'm gonna modify my original count distribution and change it into a conditional distribution that has all its probability mass at values strictly larger than zero. Yeah? So these are different models that I could put together. And the only thing I'm interested in right now is how could I fit these kind of models with R. Okay, and so again, I'm going to show you a build-in approach, and I'm going to show a do-it-yourself strategy. So if you want to do a build-in approach, I would go for the tools that are available in the library PSCL, which deals with a lot of different count models. Okay. So you can install this package, and it will give you access to maximum likelihood estimation routines for zero inflated for hurdle models with count data. So for example, if you want to implement the distribution that I refer to as the zero inflated distribution on the previous sheet, you can call the function zero infl. You can say, what is my target? That's the number of claims. What do you want to do? You want to include an intercept, you want to include the logarithm of exposure, and you want to start with as the regular distribution de Poisson. And what the routine then will do is it will estimate this Poisson distribution. It will make sure to take the logarithm of exposure into account when estimating the Poisson, right? So you can see that here, the offset is an a priori known component to be included in the linear predictor of the count model. That's completely the same as what we did before. And usually this count model is a Poisson, or it's a negative binomial regression, typically with the logarithmic link. And what we're then going to do is, in order to estimate this degenerate component at zero, and in order to estimate the weight that we give to this degenerate component, what we're going to do is we're going to, or the method is going to use the following reasoning for us. So it's going to do a binary model, is to capture this probability of zero inflation, right? And in the most simple way, the way how I did it here, I'm only going to do an intercept, but I could also put in covariates over here if I would like to do that. So what I'm having here is that this probability mass put at zero is going to be modeled with a binomial model. In this case, only using an intercept, because the hard thing here is, of course, that in order to estimate this weight P that I had on the previous sheet, this should be a number between 0 and 1. So if I freely estimate this P, then I may end up with a value that is not between 0 and 1. But if I'm going to work with this idea from what we call logistic regression, then I know how to make sure that my calibrated P ends up as a value between 0 and 1. And that's what's going on under the hood here. But I think it will become more clear if I also look at the way how I can then extract my information from the fitted model. And the fitted model here is stored in fzip. So I can look at the coefficients. I get an intercept in the count model. So that's an intercept in my Poisson model. Also takes the exposure into account. And I've got an intercept in the model that puts the probability at 0, right? So if I now transfer these estimates in the correct way, then I can get more sense out of them. So for example, in order to go from this intercept from the count model to my lambda, which is the expected annual claim frequency in my original Poisson, in my Poisson count model. So what I need to do is I need to take the exponential of this first coefficient. And then I get a value of 0.2269, right? So it's really a different lambda value compared to what we had with the fit of the Poisson and the negative binomial, because of course now we have a very different specification. And then I'm doing a very funny transformation over here. So what I'm doing here is I take the intercept calibrated in the 0 model. So that's the second coefficient in my vector of coefficients being estimated. And I'm going to take the exponential of this guy divided by 1 plus the exponential of this guy. And for those who ever took a class on logistic regression, you may recognize that, because that's exactly what you're doing if you would model the logit of P with an intercept. Then the P would become the exponential of this intercept divided by 1 plus the exponential of this intercept. So the transformation that I'm doing here is the inverse of the logit transformation. And the logit transformation, it's the log of P divided by 1 minus P. Yeah? And the whole reason why I need to do that is because then eventually it's guaranteed that my fitted probability, that my fitted weight P ends up between 0 and 1. And that's exactly what I need to have here. I can calculate the AIC for the zero inflated model. You can compare it to the AIC that we calculated before for the negative binomial, for the Poisson, etc. And we could also express the mean and the variance for an observation where exposure is equal to 1 as captured by this zero inflated model. Here, of course, you would have to think yourself first analytically, what would be the mean in the zero inflated Poisson? What would be the expression for the variance? So these expressions, I figured them out myself first analytically, and then I'm just evaluating them with the calibrated parameters. So that's what you see happening over here. Maybe it's good to continue on that with our own handcrafted implementation. So what I'm going to do here is I'm going to specify the zero inflated model, and I'm going to say, I'm going to write a function, and it should be a function that calibrates or that gives me the negative log likelihood of the zero inflated Poisson model as a function of its unknown parameters. So again, the vector of parameters here is going to be two-dimensional. I've got a parameter 1 that I'm going to use in the specification of the lambda in my regular count distribution, my regular Poisson distribution. So again, I build in the exposure measure here. And then I've got a second parameter. And the second parameter, I'm going to use it to calibrate this. I call it here P instead of the P, the Greek P, just to avoid the confusion. That's, So the P here is taking the role of the P I had in my earlier notation. And again, you recognize this funny transformation here. So that's exactly the same transformation as what I applied before. And I need this to make sure that I end up with a number between 0 and 1. That's the idea. And what the log likelihood then becomes, or the negative log likelihood, is I'm gonna have a contribution of this form. So the logarithm of p plus 1 minus p, and then the probability to see a zero outcome in the Poisson model, right? And here I've got the logarithm of 1 minus p, yeah, plus the logarithm of the probability in the Poisson model to observe a certain outcome that is strictly larger than 0. Yeah, so this is a clever implementation where I really need to make the difference between, is the observed outcome equal to 0, yes or no. So what you see here, frec and then double sign 0, it's going to give me a Boolean variable. It's going to give me a true or false. So it's going to give me a true if this condition is fulfilled. And then I'm going to use this expression in my negative log likelihood. And if I do the check here, frec different from 0, if that gives me a true, then I'm going to get this expression in my log likelihood. So this is a very convenient and efficient way to do the implementation here. But it goes back to what you originally saw over here, that essentially you need to make the distinction here between what will be the contribution to the likelihood in case the number of claims is 0, and what will be the contribution to the likelihood in case the number of claims is strictly above 0. So that being implemented, that will look like this type of expression. And if I then ask the nonlinear optimization routine to do the optimization of this negative log likelihood, then I see that I retrieve the following estimates here for par 1 and par 2, right? So if I do the manipulation, so if I take the exponential, then I get the lambda from before. If I do this transformation over here, then I should get the same value as before. So we can check this, it's minus 1.48 and it's minus 0.469. So I do hope that with the built-in routine over here, we indeed got similar values. So that's exactly the same parameterization, same meaning of the values that we catch over here. You can also compare their standard error. So here it was 0.02, 0.05. So also here, if I go via the Hessian, I'll get standard errors that are much in line with what I had earlier on. Yeah, so this is a good check with the built-in routine, with the own programmed likelihood, what I obtained. Okay. As a challenge, you could do this hurdle thing yourself. So you could try to code the implementation of the likelihood where we do things slightly differently, where we say, let's go for this implementation, which is a different likelihood. It's a slightly different model. But again, I need to make sure that the P that I calibrate here, that it ends up as a number between 0 and 1. And I need to make sure that if I start here with my Poisson, that I'm working with the conditional Poisson over here. So I'm going to give you a bit of time to look into this code, to ask your questions. And for those who want to see the challenge, I can put up the code if you want to see how that goes for the hurdle model. So these were the final claim count distributions that I wanted to add. So I think we did a nice tour of the Poisson, the negative binomial, and then some zero modified distributions. So that gives us a good idea of how that would work in